Okay, great. So I'm Stephan Sahm, organizer of this Julia User Group Munich, and every second month also giving an introduction to one of those many Julia topics. And today I picked metaprogramming. I myself did a couple of things with metaprogramming. I also hope that I can present one package of mine at JuliaCon next year, which uses metaprogramming a lot, but let's see. Still need to do a little bit on that. So today we're going to look at metaprogramming in a couple of different steps. We start with expressions. So yeah, we'll see this in the short. So you all know them probably. Then look at evil. There may be some extra information already. Not every one of you know. Then we go to look at macros, which is, as you're told, a tool many of you already have used. And then we get a bit more the second half into more advanced stuff still. Julia has a lot here. There's the generated functions, which is the base also, make it a bit larger here, the base also for Cassette and IRTools. So as always, feel welcome to ask questions in the chat. Raise your voice. If this noise is a little bit too noisy, I'm going to mute your microphone. And yeah, so right now I'm doing this with Tim. And yeah, so please feel welcome to unmute yourself and ask questions directly or just write them in the chat. I have the chat open here and take a look on it to see what's going on. And also feel welcome to answer questions yourself in the chat. So this is also really great to have a little interaction in the chat. Okay, so I founded Julian.io. If you have kind of some Julia Grim projects going on in Central Europe mostly, or kind of in the time zone, I'm very happy to help. And if time zone is not so problematic for you, I'm happy to help as well. And Julian.io in general, consultancy with Julia focus. So let's look into the expressions. You all probably are familiar with some Julia. So Julia, you can in the sense use as a calculator and store the results in variables. And with this double column, we can put something into an expression. And yeah, to the best of, to my background, the most known language for metaprogramming is actually Lisp. And yeah, Julia is kind of inherited from the Lisp background, from the Lisp past. And yeah, and similar like in Lisp, really Julia is completely tied into this metaprogramming language. So you have awesome support to get metaprogramming almost everywhere at every place in your program. We'll see this. To interact with this expression types, which actually can be quite complex, we can use the dump method, which puts us in representation. And we directly see that there's quite a difference if we place our variable in here or kind of the real term. This is because there's nothing run, there's no program executed, but really just the program itself is represented here in this expression, or what we call an expression. You see it here now that this is actually interpreted as a call of the plus symbol with the 1, 2, 3, 4 as further arguments. So this is in the head where the call is and then the arguments to this general construction. So you can imagine there are a couple of further things like macros themselves. They pop up also here differently with the macro. And instead of having the double colon, you can also use a quote, which looks a bit different, as you see. So there's a little comment in here. And also if we dump it, we see that everything is now wrapped into an additional layer, namely a block, which is another expression type in the sense, another expression header. And finally, for having this expression introduction, you can also construct them with a type, namely the expression type. And here you separate the head and the arguments you put one by one. So this splash syntax here is really args1, args2, and so forth. So one by one, you're putting the arguments. And yeah, to see kind of that we can reconstruct our expression, which we just did. Yeah, I use the splash syntax, which is also quite handy. That's already my little first exercise for those of you who are hands-on with me. So an expression, type of an expression is kind of normally an expression. And as you see, there are no further details. Yeah, so an expression type is not really optimal for a compiler. Yeah, so if you want to build some fancy code on top of it, you don't have much details here. This is it's a little bit like in any type. Yeah, you can have a lot of things in here. So this kind of a first warning that handling expressions can be quite difficult because you lose a couple of Julia's standard helpers. And even more, the exercise is here to kind of look what kind of expressions we had so far. So let me re-execute kind of a couple of them. So we only had 3. If I re-execute the colon one, we see that it's also a type expression. But if I execute the very first one, then we're going to see that it's not an expression. Most of you, or many of you may already know. It's a symbol. And actually, this is kind of a special type. There are a couple of other special types within expressions, but in general, you can actually use anything in Julia. So an expression can be kind of an intermediate part between syntax and Julia objects. And we're going to see this now a bit more in detail, namely when we try to interpolate some objects, some data into our expressions. So the easiest thing is just to use the constructor. Yeah. So here we can put not only kind of symbols, yeah, but we can really put the plus function itself, and also the 1. We don't need to have the 1 as a symbol, and this will still work. It looks a little bit different, as you see. So there's now the function is put in parentheses in front. If we use the symbol version, it has a special printing for it. It puts a plus always in between, but still it works. And yeah, and we can also to retake our result from above. Where was the result? Yeah, the very first addition, 1 plus 2 plus 4 plus, or plus 3 plus 4. And you see kind of now the interpolation syntax, which is a handy version for the explicit type construction. And with this with this $sign, we can now interpolate is the technical term, insert any variable which we have into our expression. So this is the key difference. Here it is a symbol, and here it's really the object itself. And we can use this for any object which we want. And yeah, the little syntax that you've seen this, there is also support for several arguments. And here we are now reconstructing our plus, where the arguments have been stored in the standard tuple. So this is really Julia object, and we're now constructing an expression out of it. Okay, so that was my little tiny intro to expressions. Are there any questions from your side? If you have later some, just drop them. Next, we're going to look into what we can do with expressions. Having expressions just for having expressions is not of much use, but we usually want to run them. So if we have an expression like this one here, which we constructed, we can evaluate it by using the eval function. And next to the function, there's also a macro version of it, which gives us kind of some superpowers. Writing normal code, but using the interpolation as well in this normal code, which you've seen above for creating expressions. So here we had a variable which had the name of the actual symbol name, and we called now nice. And yeah, and then it was actually evaluated into our global namespace, and we could access it. This is a really powerful thing. And yeah, and you'll see kind of a couple of difficulties with it, restrictions. But so far it's really mighty and you can use it in your code almost wherever you want. Okay, so little exercises here. So let's evaluate a couple of expressions. I haven't made a little space here. So if you want to add an extra cell, it's always the plus here. And I haven't told this, but if you want to run a Jupyter Notebook cell, it's always the run button here, or I'm always pressing Shift Enter. So let's see kind of a couple of parts. So if we can really evaluate anything, and I'm totally not creative. So we can really create kind of whatever we want. I think most often it's easiest to write it with the evil sign. So you don't see anything fancy here. We can really plug in any function which we want. Yeah, so this is, if you use the evil, it's sometimes really hard to get it into your mind. Where's the difference between an expression and something which is just run, because it already runs it for you directly. But still, it's really a powerful tool. Okay, let's go on. We have a good question, thanks. I always hope for some questions. Can evil be type stable to use inside functions? Whoa, this is a very advanced question. And well, I'm going to think about it. I'm going to think about it while I'm proceeding.
So just to explain myself with the question, the question is, can you pass in an expression somehow to a function, and when you call a val inside this function, will it be able to do type inference just from the expression to get what is really going to be the result? So I tested a little bit with a simple function. It didn't manage to do it.
Yeah.
But I'm not sure if that's the general rule. So that was my question.
Yeah, so inference is a super tough thing. I myself am still struggling with it. Yeah, so you usually have support kind of if you just use it inline and all information is available. So I think it's similar like with anything else in Julia.
Because you mentioned that there is something like any before, and that's what I understood. So how did you
Yeah, indeed. Yeah, so if you work with expressions directly, then the compiler has little knowledge about it. But usually the expression is then inserted into code where it's interpreted right away. And this is kind of a compilation step. Yeah, think of it like compilation. And yeah, okay, so this is indeed bad. So this is my usual mini test of operation. And I would have expected that this actually knows about this. And and would have been bool. Yeah, I wanted to have bool. Thanks for the question. And sorry for all those who feel a bit lost right now. We're going to continue in a second. Okay, so I have to admit, it seems like even this case is a bit tough in inference. So what is usually preferred is kind of to have probably one method which generates some code, and then after it, you are going to use this code. So this is probably a good general heuristic for you to get kind of good type inference, so that you're not intermixing it with the real code you want, but really have a first stage where you evaluate whatever code you want, and then after that you're using all this, and then it should be kind of standard normal Julia behavior. And this combination of evil with a normal function invocation is apparently not optimal in inference.
But you're not using evals, you're using a macro, right? So
yes, but it's the macro is translated to eval itself. So wait, let's I need, and with the eval function it would be like this, and it's still any, yeah. So a pity, but yes, it's not 100% supported here for type inference.
okay. Yeah, I don't understand why that last one didn't work, but okay. Why don't you move on?
Yeah, let's move on. And if we have time, we'll take another look in the end. I like these questions. Okay, so what I want to point out is that the evaluation here is always bound to a specific scope. So every Julia interactive session has a module. I think it's called main anyway. It's the thing which you have right away. And yeah, main works at least. Yeah, so we have access to our variable which we created. We can also create another module, my module, for example, and we can evaluate within this module. So this works. And this is actually really important because depending on where you run your eval, you usually want to evaluate within the model, within the module. And with an eval macro, it looks a little bit different. So there we separate things by space, but we don't need to. We can also separate them just by comma. And yeah, and there it's just the first argument. So the macro version is defined centrally, and yeah, so this is the way you can use it, and it's just important to keep in mind. Then I want to point out some limitations, and I hope this is a little bit enlightening for those who haven't seen this. So it's quite tough to have an eval function and still create optimal code. So this is related to the question which just came along with the type stability. And yeah, and I guess this is kind of the detailed answer to it. And yeah, actually, Julia has a concept called world age, which tries to solve this problem, like when it can compile your function to the best optimal machine code version it knows, and when it cannot. And yeah, the difference is called world counter, and the world counter is increased every time we evaluate a function. So here we generate a function which multiplies the given value by 2, and yeah, we see that the counter, it's cryptic, I admit, but nevertheless you see it increased by 1. And interestingly, if we kind of executed something else, like I don't know, a simple assignment, then the word counter does not increase. So global variables are really supported in a general manner, which is also one of the reasons why they are not so performant. But if you write a function like we had this, then we see again the word counter increasing. And yeah, this was my little exercise for you. So give it a couple of tries. So if we eval true, then the word counter stays there. If we just evaluate kind of an arbitrary value, then nothing increases. Yeah, it's really only increasing if we define a function. And yeah,
that makes sense, right? Because you're not changing the namespace unless you're writing a function, right? So that's the namespace is not changing.
Thanks for the comment. A little bit, yeah, but this in a sense also changes the namespace. But global variables are just dealt with in another way. They are in a sense assumed to be there if you use them, and the error will be thrown if you try to access them and they are not there.
Sorry for the interruption. Yeah, right. So global variables are in the global namespace, and so that's always, sorry. Yes.
Yeah, so this is indeed a little bit more detailed, yeah, and it's an interesting detail. So global variables are resolved like if you use them, and global functions are really resolved already on the compilation step. Yeah, and if it can't find the function, it cannot compile your code. Okay, let's get deep dive a bit more. So world age, what does it mean now concretely? And there I found a lovely paper where there's a lot more detail available for you, and one quote out of it, which nicely summarizes the meaning for us here. So I'm quoting: semantically, newly added methods, for example, those defined using evil, only become visible when execution returns to the top level, and the set of callable methods for an execution is fixed when it leaves the top level. So the top level is really here, what we have here, our interactive session, for example. And if we leave it, we are going inside a function. And I think this explains why the type inference failed in the first example, because it already wanted to compile a function when we went into the function, when we started to execute it, but there the evil was not executed yet, hence it needed to infer a more generic version of the function. And as soon as the evil hit, it was already too late because we've been already using the function. Okay, in my words, whatever function you create within the function is not visible within the same function call. And as we've seen, this is even a bit more generic, like with this evil of a simple true value. But here, these are also very enlightening. So if we have a function which in there creates a new function, and we call it, then we're going to get the typical failure in this regard. Yeah, and I hope if you're seeing this now, you're no longer afraid of it. If you see this the first time, it's always, whoa, what's going on? So it's telling the applicable method may be too new. We are running in world age, and now there comes a lovely number. I was not able to get this number with a simple function. While the current word is one more. And and the solution is really in this scenario to call it again. So now the function is generated. We work again at the top level, and we executing the code. So now we have access to the new world, and and it works. So I hope this is enlightening. Executing the second example here. So if I just evaluating a variable, then everything works on the first run. So the variable resolution is done differently, namely just kind of looking it up in runtime and throwing an error if it's not there in runtime. There's another question. By the way, doing my module new var equals 3 gives error because we cannot assign variables in other modules. Interesting to see. You can bypass this with evil. Thanks for the comment. Yes, indeed. I am using this myself. And with the new Julia version 1.9, I've seen that there's also some additional support for updating global variables in other repositories and other packages. Thank you also for the hint. So just wrapping the counter into an integer gives already the nice representation. Okay, finally, if for some reason you really need to invoke the function which you just evaluated, there is an invoke latest helper function with which you can bypass the world age mechanism. So this gives you power, flexibility, but of course the compilation is worse. So the performance will be much worse of your function. So try to avoid it, but it's good to know that it's there. Okay, this was my little part about evaluations in Julia. And the Julia notebook, can you go back to this execute twice example?
Yes. Yeah, I'm just trying to understand here. So you define this function, and you're now in a different namespace. I got lost as to why it didn't work the first time, but it worked the second time.
Yeah, thank you so much for asking. So this is really a bit tricky for my own mind as well. So just let me repeat here. So the thing which makes the difference is if we return to the top level. Yeah, so if we get to the top level execution, then Julia recompiles your code. So it will kind of check all the newly defined functions and create new versions of your code.
But how did you get out of the top level? Just by defining the function?
Just by going inside a function. So as soon as we call a function, yeah, we're going out of the top level and we get inside the function. So the first time, there was no general advice anywhere defined in the top level. And yeah, we enter the function and yeah, no way. Yeah, the general advice was not found when we entered the function. So yeah, the compiler completely ignores it. And inside the function, we generate now our our little advice here. And yeah, so if we have run the function once, then the top level surrounding changed and the new function is already there. So on the next time recompilation kicks in, it finds the function and gives us the result. And yeah, and also compiles it. So type inference is optimal.
I just needed you to explain it a second time. I got it now. Thank you.
Thank you so much. It's really one of the most tricky parts of today. Okay, great. Yeah, any further questions? Always feel invited to raise your voice. The next topic I've prepared here are the macros themselves. So macros are now a natural next step. We've seen the expressions and we've seen the evaluations, and then many times you want to do both at once. And this is kind of what a macro is about. So here I've started with a little macro, the timed macro. So it's a little bit more complex, but you easily get it. So there's a time function in Julia. Let's run this first. This is already there, and it gives us the current time in seconds. So from, I don't know which time it was, yeah, from some fixed standard time, the amount of seconds which have passed. Okay, so having this, executing this before and executing this after, then we can kind of compute the difference and print it. The macro itself looks a bit like a function, but calls macro and has also arguments. The arguments, they are now always, in a sense, expressions. And hence we can take them, whatever it is, we can interpolate it here, and we get a big expression where we have our computation around. We store the result of our inner evaluation and return it in the end. So if we call this macro, we call it with an add before. You've all seen this, so this is how you construct it. And this is because we need to distinguish them from normal functions. This is just a design decision in Julia that macros and functions are two different things, and macros are always prefixed with an add. Yeah, and this is kind of a nice example. So you see that our sleep function in Julia kind of works. And of course, there's some randomness to it, but yeah. And it's also very precise. We can also time really tiny things. So this is the easy way. Yeah, so my little exercise here is to time kind of a couple of things. So feel invited to really try it out. One thing which you think takes for ages, and you see it's running blazingly fast. But there's a difficulty because we are mostly running it on the global namespace, on the global REPL. Let's creating a random example. So if you want to build a larger block in Julia, begin and end are your friends. So there you can create some extras. I was too motivated. I fear my session is kicked now. Okay, I could still interrupt it. Okay. It's interesting. Okay, just a few. Yeah, there we got it. Oh, that's interesting. Okay, that's quite a large sum already. Okay, so getting back to the topic, it's very interesting to look at what a macro actually does. And there's one helper macro for this. It's called macro expand, which shows precisely what the macro is returning before it's evaluated. And you see that it's not the same which we've been written above. There's a couple of hashtags here, yeah, some random numbers, and this is really part of the macro, yeah, helpers. So the macro concept, and this is called hygiene, macro hygiene, so that the variables you've been using in the macro are not interfering with the code where you run the macro, so that you can really assume that things are separate. And many times, like in this timeout example, this is exactly what we want. We had a variable before, and we didn't even thought about whether it's a variable which could pop up in the surrounding context. And it turns out we were fine. Yeah, so we didn't need to bother about this because the macro hygiene automatically renamed this to a variable name which isn't used anywhere else. And same for the other variable names. Yeah, so this is important to know, and there are a couple of situations where you don't want this, and there are ways around this. It's the escape macro, and the escape macro really marks something or texts something to be inserted directly. And yeah, if we run this, we see that we really have created our variable like we named it, and we can access it. And sometimes you just want this, that you help creating a couple of variables and you want them to be named like you want. And that's actually a reverse way of doing it, which is also very important to know. That's called a gensum. With the gensum helper, we can simulate what our macro hygiene did for us automatically, namely creating these pseudo variables. And with this generate symbol helper, we create a helper variable, and now we can escape the whole expression which we return, which looks a bit nicer, at least from my feeling. And now we use the interpolation for our variable. And yeah, and everything else is really inserted directly. And we see that this also works. So if we take a look here, we can also inspect that our gensum helper really created our little helper variable with a random new name. Okay, so this was my little part about macros. Going to have some packages. Little exercise here. It's interesting to see a couple of real-life macros which are already there to get an idea that some things are probably complicated, but some are not. And for example, the gensum helper is really super basic. So yeah, so this is expansion of it, and you see it really does almost nothing. It just creates the gensum on top of the within the macro it was escaped, but so the literal name, and it returns the default return value nothing. Yeah, I got a question. So just to go once again about the gensum macro. You see the gensum macro is really just a helper around the gensum function. Yeah, so let's maybe execute the gensum function. So if we go to the gensum function, we see that we create a symbol. And if we do it again, we see that we create another symbol. So this is, screen sharing is off.
It flashed off, but came back on for me.
Okay,
so
thank you so much. Yeah, this is really important information because I myself, I can speak forever without noticing that my screen share is off. Yeah, thank you. And I'm happy it's back on. So the gensum will create a new variable every time we create it. So you can really be sure that this is a variable which is not there yet. This is the key idea of this little helper. And with the gensum macro, we just save us a couple of strokes and make our code a little bit nicer. So here, this is really the same as we have seen, like calling the gensum function on the helper string. So these two sides are the same. And having this new variable, we can now kind of use it really to store whatever we want to store. So this, a tiny example, no use here, but you see the power of it. And having this variable in here, which is already a new variable, which cannot interfere with anything else, we are free to escape the whole thing which we return, so that it's not, that hygiene is not applied again on it. So we've been taking care of hygiene, how it's called, so making sure we are not interfering with the outside code in unintended ways. And and circumvent the standard hygiene by wrapping everything in an escape function. I hope that explains it a bit better, or anyway, sometimes it's just good to hear it a second time. Just taking some drink. So these are still quite basic macro tips I'm giving you. Still, they are quite important because this is a usual thing which you will encounter if you write a macro. If you want to do a bit more macro manipulations, there are a couple of helper tools out there. Just mention two here. There's the IRTools.jl, which is currently maintained by the Flux machine learning community. And it provides a couple of functions, functional like tools, where you can manipulate your macros in some ways. You can take a look at the documentation. It's widely used. And I myself was not so fond of it when I first really tried to get my complex macros out there. And to get a bit more grasp on it, I really wanted to have some more object-oriented style, so that I can say I want to parse a function, or I want to parse a call, a function call. And these things are then wrapped into my little package expression parsers.jl. And maybe most known packages which use this is my own again. So really spread the word, it should be used more. Where traits, another package of mine. This was the main building, the main development where I also developed expression parsers for it. So check out both. Totally different approaches to working with macros, and it's good to have them in your tool set so that you don't reinvent the wheels if it's not necessary. Because of timing, I'm not going into the details. Bear with me. We may have another session on them. We continue with some other basic stuffs. So we now get to the, I would say, most powerful concept in the Julia language. And these are generated functions. You can think of them like a macro, but they have the standard function interface. And if you've kind of taken intro to Julia and went on to the meta section, you already have seen them because they are really also part of standard Julia. This is not a package, but really a macro which is provided by Julia itself. And and the easiest way, it's also another twice function to see how it works is by really kind of printing out. And printing is actually not so easy here because generated functions are like macros executed on kind of compile time, so just in time compilation. And in this in between layer, we don't have access to the standard printing system, but luckily the core comes with another print method. It's really different one, which is more bare bones and works also in this context. And if we call it, we see that it will output the X, but it doesn't print the value, but just the type. So this is really the way it works. However, then what runs is just the right thing. So the name is the same, but you see we've been returning an expression. So we are not accessing the X, which comes here as a variable, but we just use it as a symbol in here. And this is the right interpretation. This is the right way to work in generated functions. You use the same symbol you use here. So if I've been using a Y, And then I would need to use a y here. So this is really, the symbol name is taken from the function argument name. And this is very handy because it looks like the same code, just you wrap it into the expression column. So yeah, it looks really nice to me. Oh yeah. Recording is still running. Yeah, thank you too for joining. I'm glad to have so many interested people here. Okay, if we run it the second time, yeah, we only get the result and we don't get the println any longer. And this is the same like for the macro. This macro code, in a sense, this generated function code was now evaluated and will no longer run. So we now use the evaluated return expression. And hence this one is no longer given. And if we re-execute our function, yeah, then of course it's going to reprint it because it was overloading, yeah, replacing the previous one, and now it generates it again. So my usual way how I access this type information is actually let me type by using where type variables, and just that you've seen this. So because this is kind of the opposite of or the other type of a normal Julia function syntax, you can annotate it with a concrete type or kind of a type variable. And the cool thing, the maybe surprising thing is, is that they are the very same. Yeah. So you see that the type information is in the sense correct. It's really an integer type. It's just the variable which is wrong in the normal function sense. So the type information is completely right, intuitive. And this is why I'm usually not using the variable. So I myself, I make my life a little bit simpler by just going the type way. Yeah? So I have the type here, and this would be the same in a standard Julia function. And yeah, and then I'm deciding on which code I want to generate given the types. Yeah, and I myself like to read these functions a bit easier, a little bit. Yeah, it's more comfortable for me reading these functions this way. Of course, the syntax is more complex with the where syntax. But yeah, okay. So using this. Okay, so this was a kind of just-in-time version of evil. If you think about it, with the evil, we had to really run the code. We really had to enter a little sentence saying, evaluate this or that. And then after that, we can generate something. And we can run some other functions which use the generated functions. With the generated macro, our generation is really done automatically at the right time by the compiler. So if we are not running this code, nothing will be generated. And if we run this code with a different input, then a new part will be generated, now for string. And it's really generating it every time again. It gets new type information and yeah, and needs to compile a new function. And this is just the perfect in between. Yeah, you get the right there where Julia compiles your code just in time, and you can give it some arbitrary expressions which it should compile for you. And yeah, I hope it was not too confusing right now. Yeah, we see some of this power in a second with Cassette and then IRTools. We had the macro expand helper to look at macros. It would be nice to also have a look at what generated functions are doing. And there's unfortunately not the very same tool for generated functions, but we have something okay-ish. And this is the code lowered function, or the code lowered macro. And this will give us access to one of the intermediate representations which Julia uses. So it's not the very Julia code. You see, we have some % variable names here. Yeah. So it's not the very, very same, but we get an idea. Yeah, so it's not too much machine code already, and it's using our commands. And we see here that it's really just multiplying it with also the y variable, which we've been using. And yeah, I want to show you one example of such generated function, which I wrote myself. It's a struct equality package. And the background is that if you define your own version of a struct here, for example, one with an abstract array, and yeah, you compare them, then the standard comparison between arrays would return true, but the default version for a custom struct returns false. And this is really difficult. So it goes against intuitions. And if you stumble upon this, there are a couple of solutions, and one is struct equality, which defines a macro and a generated function, a struct equal. So importing those, we can assign the macro with our type, which would generate some helper functions, and then everything works like expected. Let's take a look what this does. So we can macro expand our struct hash equal, and you see it's a little bit wrapped. There are some blurry comments, but yeah, if we cut off here, we see that our hash function is referred to the struct hash function, which is a generated function, and the equal is referred to the struct equal function, which is also generated function. And yeah, we can inspect the generated function, and we see code lowered with code lowered, and we see that it's really compiling the ideal version for our struct. We get the property value from the first and from the second, and then comparing them. And yeah, this is just done by inspecting the types, getting the field names, and constructing the code. So I think this is a quite easy example. You can take a look at the implementation at GitHub if you're interested. There's some type tools involved, but in general, it's quite simple. There's a question. What are the most popular use cases for generated functions? So yeah, generated functions are there to compile specific code for you. So there are some cases where just the function way would involve some recursion, some loops, some for loops, some while loops, or like call recursions. And yeah, it's not always easy for the compiler to make this into optimal code, but often it really has to refer to some recursive code, which then will be a bit more, a bit worse in type inference. And if we really care, we can kind of use this generated functions to create specifically simplified versions for certain cases. Like a typical thing is if we usually combine things, arrays, or better say tuples of length up to 30, we can precompile specific versions for all these tuples. Of course, it's a little bit more code to be compiled, but because we are using them so often, we get quite a performance benefit of having special code for the small versions, and only general code which uses loops and so forth for the tuples with really long lengths. So this is one example which you also find in the documentation. Here's another example, is to write some further meta programming on it, and really get kind of some magic into Julia. I would say then if there are no further questions here, let's continue to really one of the most powerful examples of generated functions. And this is Cassette. Cassette is quite old already in the Julia ecosystem, and it's one powerful generated function under the hood, like we'll see in a second, which then allows you to do metaprogramming without actually using expressions. So as I already told you here and there, expressions can be quite nasty to work with. So this is a type which can have almost anything in there, and it's hard to get more type information on it. And Cassette allows you kind of to tweak the language without really using expressions. I will see this in a second. So this is we're going to a couple of mini examples. First, we're using Cassette, but we're actually always using Cassette with the qualified version. So the context macro of Cassette builds us a specific type. Okay, this is actually not needed, the semicolon. And with this specific context type, we can then call Cassette's central overdub function. And the overdub is related to the package name Cassette. So we are really re-recording what Julia's doing. And if we execute this line, we see that it takes quite a while. Oh, it was actually quite fast in this regard. Oh, okay. Okay, some later might take a while, but yeah, let's see how powerful our machine is. And you see it's doing just division, 1 divided by 2. But under the hood, something completely different is done. So if we get the code lowered of 1 divided by 2, we see pretty basic things. So we have some typecasting, which is actually also interesting to see that this is done because we are just entering integers. And then we have the division. So if we would have directly put floats, then our code is even much more performant. So yeah, that's good to see. If we look at the overdub version of it, it's much more complicated, but actually not so complicated. So this is thanks to this little example I also took from the Cassette documentation. So we see that there are a couple of fields which are first accumulated, first assigned. So X and Y now are our 2 arguments probably, and we have our self, which is the function itself. So this is the division function. And then we have our calls. We have first the float call. Let's get back here at the top to really see the original one. We have our float version. And then finally, we have our divisions here. And we see every time there's a pre-hook, then there's an overdub, and then there's a post-hook. And the overdub is kind of the central execution because you see it's then assigned to the variable, and the post-hook gets the variable information in addition. So these are 3 hooks you can have in Cassette to get extra features into your code. We will see later on precisely how you could implement this, but I think the idea is already clear. So we have the generated function, which gets in our argument types, and given our argument types, it must be necessary to build such a code. And there are some fancy functions to it, like what you need to really build such a code, but it's possible, and Cassette is doing this for you and building up all these hooks everywhere, so that now having Cassette, you actually do not need to do the generated function style, but you can now use really standard method overloading. Let's take a look at it. So I hope this connection to generated functions is already clear, and that Cassette does some helper functions, inserts some helper functions for us. And we now only work with the overdub central algorithm. And this is one tiny example. We build now, again, some custom context. We want to replace sine with cosine. And this is really like how we do it. We've seen that overdub is just called with the standard arguments, where an extra argument is really just the function which is called. And we now have our type double column, and we only want to dispatch on types of the sinus function. And this is the type of the sinus function itself. That's the easiest way to type it. And it has one argument, one simple argument. And what we return is just in this part minus cosinus, to easier see in the next line that it worked. So, and now we can call it with the overdub function again, and we now, for example, call it in the sum. And for each element in this random 10-element vector, we are now computing cosine plus sine. And because sine was replaced with minus cosine, it should return 0, and summing up over zeros returns also 0. And now we have the cassette overdubbing system working, and we see, yeah, it's 0. And this is the magic of cassette. So with this overdub, we've replaced all the inner code with some new code, which has all these helper functions, which we then can use with standard dispatch. That's really nice. And I have a little, this time a bit more involved example here. So the little task here is to build an overdub which ignores println statements. And some helpers around it. So we have a println context, and then we need to implement our little overdub logic. And then there's an example function which taken from the set documentation, which prints out a couple of things while adding. And our goal is now to just call this function with an overdub, cassette overdub, and ignoring the println statements. Okay, so give it a try. Yeah, so the core idea is that it's very similar to the example you've already seen. So hence, let's take copy and paste on what we've been doing above. Okay, so having this example from above, we see, okay, first we are using another context. So we should change the context type here. Again, we don't care about the actual object itself. We just want to make sure that our code is only called if using our special println context in this, hence we dispatch using this context. Okay, and then we have currently a sine function which we replaced, and now we want to replace the println function. So let's give it a try. Yeah, now it's the question what we want to return instead. So what we want to compute instead of our println. And and actually we don't want to compute anything. So nothing is the standard return value in Julia if you do nothing. And this works here. So there's still kind of a, you can still make it a little bit more generic, I think, but it should be enough for our case. So if we now, we have it on the same page. If we now run it with the cassette overdub, we see that our println is actually ignored. And this all without a single expression. So this is really powerful tool, good to know. So we see we have our return value, but ignored everything else. Of course, it's still tricky. You need to know the precise functions which are called. You really need to have a good understanding of what's going on, so that you're not overdubbing something completely completely disrupting. Okay, so there's a little extra challenge for those of you who want to give it a try. So if you want to have a solution, this is an example taken from the Cassette documentation, but there are a couple of sides to the Cassette documentation, so it may not be that easy to find. So the original example where I made this little example from was, in addition, collecting all the println statements within the context, and then later on returning the value plus the collection of println statements. And and the general mechanism here is that we can actually assign some metadata to our context. So if we create a context, in our example above, we've just called with no arguments, but we can create one with the metadata argument where we can put whatever we want, for example, a dictionary. And then So it's really the same context. Yeah, we are not creating a new context. The standard cassette context already has this feature. And this one, we can really override everywhere where we want. And yeah, and it will just work because it's now a mutable state in the background, which we can work with. And now you can overdub your mechanism, not only by just assuming you have a context, but now you can also really get your context and do something on your context. So yeah, you can now change your context metadata. And collect whatever you want. Yeah. Now, example, what's the key? Yeah, and do whatever you want. And then finally, because it was mutated, you have it on the context itself. So you're doing stuff, blah, 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 blah. And then, yeah, you have the context here, and you can extract the context metadata then after the function run. So this mutating approach to get a further state into your metaprogramming, your cassette metaprogramming, I think it's quite easy to use. Oh, okay. And yeah, and definitely good to know that this feature exists. So my notebook connection just broke down, so I need to scroll back to the link. But let's first look about the question. Would be curious to hear a bit about the performance impact of passing through Cassette. Yeah, so Cassette is adding all these extra functions. And yeah, if you're not using them, then the compiler should be smart enough to compile away most of it. Of course, so I think if you now use Cassette on a normal basis, the biggest impact you are going to see just when doing it the first time, because then Cassette is building up all these generated functions. So they're building up all these new code and doing a lot of logic, a lot of computations to actually create this code with all the Cassette helpers. So this is taking time. And yeah, you're definitely going to feel this, this translation of one intermediate representation to another. But then after it's translated, the code is really as fast as you would have written it yourself. And yeah, you've seen a couple of extra calls, which we've done. And yeah, and probably, it's a good question. I'm not 100% sure. So it would be great if the Julia compiler sees that this can be skipped, but probably it cannot, because if the function is not defined, it will throw an error. And if it's defined, it's called. So you will have a small overhead, like the function is called and returning nothing. And either the Julia compiler is smart enough that if the function, to see that the function called has no side effects at all, so that it's safe to just skip it. But I'm not 100% sure about the Julia compiler at this stage. So probably some optimizations can be done, but some others are probably hard. So I would expect also a little performance impact on the runtime, but it should not be super big. Okay, so now I try to reconnect. Just for those of you who get the same problem as I do, here again the link. Thank you very much for the additional questions. Just saw it. Could you show again how you remove the print statements in the add function? Yeah, so this is indeed magic a little bit, and I haven't gone upon it. So the key aspect is actually recursion. And this is pretty simple, and it's so simple that I myself skipped it a couple of times when I first went through the cassette and intermediate representation route. So if we go to our cassette example again, so we need cassette definitely, and we have our println context. Oh yeah, you see, this is the extra exercise when using some empty spaces, your space. So I'm cloning my solution from there. Yeah, so we are overloading this specific version of overdub, which is specific to having the println context and to having the println function being called, and actually also to having only one argument. So this is the version which we overload. So if we call our rand just directly, it does the normal thing. And if we call overdub, let's directly go there. Yeah, let's see what the overdub does. So the overdub now gets our function, yeah, and rewrites everything with the prehook and overdub calls. So in this regard, yeah, it's actually, yeah, where it is. So we have first some string constructions, and we are recursing here into the overdub itself. Yeah, so this is the very same function. We are starting with an overdub, and within this code, we are also again going into the overdub function. And yeah, recursively doing what we see here. But actually in this case, it's already simple, or a bit simpler. We can directly see that we are calling already in the first layer an overdub with our specific context and the println. So this will be exactly our function call, because it has just the right specification, the right type specification. So it's not using the general cassette overdub version. This is the fallback in the sense, but it's using our specific overwritten overdub version for exactly these arguments. And hence it's not doing anything here. So it's really just calling this overdub function and yeah, returning nothing. And same then later on here on the final one, overdub println. And if this would have been in another function, then still works, because overdub calls itself recursively. So if it looks into another generic function, that just does the same as you see here. And yeah, at one time, it's going to see this function call where the println is combined with one argument, and sees I have a special implementation for this case, and calls the special case as Julia's standard multiple dispatch algorithm does. So this is really kind of giving you the power of multiple dispatch, or using the power of multiple dispatch to do meta programming. Okay, so also important that you've seen the metadata key so that you can collect some information about the code which was called. And in this little example, it collects the functions itself, the function calls. So because you have access to the println function and what it would have been doing, and you just can store this everything in this mutable state. And the dict is now just the most intuitive mutable state. Okay. Thank you for the question. If there are no further questions, we have 15 minutes left of my normal 1.5 hour timing. And I think this is kind of enough, I hope. So let's start with IRTools. So this is, I titled this Generated Functions for Intermediate Representations. This is one of the background tools which are used in the machine learning flux system. And it's used for building up the gradients. So this is, in the sense, another example of using generated functions. Zygote builds the gradient definitions using generated functions. And specifically, they build the IRTools.jl package. And yeah, so having a little dummy example. So there's a super complex way to compute the identity of an integer. And because it's so great to know what the output is, I use this now as a little example. But you also see that Julia is not smart enough to see that this is an identity. Yeah. So this is kind of a normal thing of coding. Even if you can show it now mathematically or something, it's really hard to do this generically in some compiler version. We've seen the code lowered already, and this is what I'm starting with. So this is itself an intermediate representation. It's not the original code which we put in, but it's already put into something else with go-to statements, with these add things, these person things. So there's a lot going on. And I have to admit, I've never really worked with this code information because I directly found IRTools. And with IRTools, the code looks a little bit more intuitive, at least to me. Yeah, and I think to many others as well. And this is one of the reasons why IRTools was built. So here we get another intermediate representation, which is structured into blocks. We haven't seen this on the code info, or we've seen this a little bit. We have 1 and 2 and 3 and 4, but they are not the same as here, as you see. So the one has 4 blocks, the other has 3. And the IRTools representation, it's really kind of simple. Every line is just one function call. Here the colon, then the base iterate, and then at the end of every block we have a branch condition. So we go to another block and pass some arguments in the functions and have maybe an if not condition, which is here written unless. So this is if not, and I myself prefer if not, but okay, they have written it unless. So you can think of every block really just as a small mini function, which branches then to another block. And then some of these branches are actually no branches, but a return. So in total, this is a function. We enter at block 1, get in these arguments, and then go through all these blocks like it's written here. So I've worked a bit with these representations, and still there are kind of a couple of things you have to keep in mind, but this is kind of the complexity there is. So it's, in a sense, standardized and kind of nice to work with. You get a couple of extra helpers. And yeah, so you can access the blocks, you can access arguments of a block, you can access the branches of a block, just one power function. You can also access the blocks which refer to your block. There's also a successor block. So you see in this part, so we had the block 2, and so we construct the block 2, and we see that the block 2 actually refers to itself. Yeah, we also see it here. But there are a couple of help functions in this toolbox, which are really nice to work with. You can also create a variable, which is actually just an integer. And yeah, then we can also change our intermediate representation. This is particularly useful, particularly powerful. So what we use here, we have our intermediate representation. This is really the thing from above, just store it into the variable. And then we use index syntax with a variable to get to the line of the variable. So in this part, we are getting this line. We're now replacing this with, so here you need to use the IRTools helper xcall. But in xcall, you can again use kind of symbols or objects, whatever you want. So here we use the plus instead of, we add 2 instead of 1. Yeah, so you see this is kind of the very same, but now we add 2. The original code was like this. So maybe not the prettiest, but this call syntax is really nice to handle, and the pretty printing then looks good. And yeah, now you can kind of think about what it's now doing. So we changed this little line here where we always added +1 in the loop. And now we add +2. So our little identity is no longer an identity, but a twice. And yeah, so there are a couple of ways how we can see this. IRTools provides us with an eval evaluate for intermediate representation, for this intermediate representation, there's one extra we need to know. This is the first argument is exactly like a cassette, the actual function type. So because we don't need it here, so this would be then, what was the original function? Int identity. Now I now remember it. So this would actually be int identity. But for our simple case, the function type is not used at all. So we can also replace with nothing. And we can evaluate it. And we see now it's really kind of twice as much, because for every count, we added 2 counts. And we can also put this into a function. So IRTools provides a func helper, and then we call this as a function. And again, this is kind of the first argument is the function type or the function itself. And hence in this simple example, usually a nothing is inputted. So just to note, in Cassette, you can actually do similar things on the code info object, which we've started with. And that's called a contextual pass or compiler pass. And so it's a bit more tricky to work on code info objects, but it's also possible. So the intermediate representation here from IRTools is a bit easier to work with, and also well maintained, as it's part of the Zygote and Flux ecosystem. And there's one last thing I want to show you. This is the Dynamo of IRTools, and this is the actual thing from the title. So this is now like a generated function, but instead of returning expressions, we are returning intermediate representations. And this has a couple of benefits. It's a bit easier maybe to read, but let's see. So it's really kind of similar. We have a macro in front, and this time a Dynamo. And we again get a function, and I now call this inspect, a couple of arguments. And we use again core println, because this finally is going to be compiled into a generated function. So we can again not use the normal println statements, but we need to use core println. And we need to return an intermediate representation. And this is kind of the standard way how to construct the default intermediate representation. Okay, so we can inspect what our Dynamo would do on prod 1.4, what it gets. You see that the first argument is the function name itself. So this is really like in Cassette. And then we get the type. It's all about types. It's a generated function about the second argument. And this type information, as you see, is then put into the ER, intermediate representation helper, and this constructs the intermediate representation. Okay, so let's execute it a second time so that you see this is really, this println statement is really only done the first time, and then everything is compiled. Okay, so this is in a sense really just like a generated function, but with a different return type with an intermediate representation now. And this is one example taken from IRTools, which actually uses macro tools. So intermediate representations in this sense work very similar to expressions itself. And here's one little example where we replace multiplication with sum. So remember, you could have also done this with Cassette without using this intermediate representation or macros. But we can now do this also with IRTools. So we construct our intermediate representation. So what we've just returned before, we now take kind of as our first step, and then we rewrite our intermediate representation. Because it's relatively straightforward and standardized, it's relatively easy to change things on here. And what we're now doing is just to change multiplication with plus. It's a little bit more complex as the global ref. And this is the curse of expressions. There's a lot of little extras here and there you're going to get to know if you work with expressions, and similar it's here with intermediate representations. And one of them is a global ref, which refers to one of these global variables. Okay, let's run this. I have a little warning because the block is used by both macro tools and IRTools, but we can see it working. So now we replaced multiplication with plus. So 3 plus 3, 6 plus 4 is 10. And yeah, and the nice thing now is that we actually have full support. At this level, we can use again code intermediate representation to get the really precise intermediate representation which were returned. So this is in a sense a bit more completely supported. Where the generated function, you do not have access to the expression it returns. Here, you really have access to the intermediate representation it returns. However, it's not yet as recursive as our cassette example. And this is I think my very last little example, now how you can get into the recursion. So this is really the multiplication of it, 1 to 4. So this was the original output. 24 is the multiplication of 1 times 2 times 3 and times 4. And this is one way now to get the recursion in. And what I'm doing here as a last example of today is actually to define a simple version of what we've been seeing in cassette. So this is now called my overdub because it's in a sense implementing a simple cassette version. So we get the intermediate representation here. We might make a first check whether it's nothing, because sometimes it doesn't work to get the intermediate representation of a call. And then there's a fallback, which the IRTools handles for us. We just need to return and say, okay, we don't know what to do. So this is handy because there are always edge cases also here. And in this regard, the edge case is taken over by the IRTools. What we're now doing is that for every statement, for every variable here, we are now checking whether it's a call statement. So this is really just expressions here. And if not, we continue. And if it's a call, we are replacing this call with the recursive version. Namely, we call again my overdub and then place all the arguments here. So sorry for being a bit quick on this one, but I hope you get the idea that we are just replacing our function code with the version where we are not calling the function itself, but we're calling my overdub of it. So really just like you've seen it in cassette. And actually there's a short version of it. If you don't write this yourself the next time, you've seen this. There's a helper called recurse, an exclamation mark, which does the same thing for you. And now we can do just like we've been doing in cassette. Yeah, we have a my overdub and use again dispatch on it. But yeah, instead of cassette where we had another context in the beginning, now we created our special my overdub function, and yeah, and have the function type as the very first argument. So it's in cassette we had this context. Yeah, remember the println context, and otherwise it was the same. And now here with the Dynamo, there's no context in our mini example, but yeah, we can still use the dispatch like it. And now if we use it, then we should receive a 10. And you see what I've told before. So it was taking quite a long time to actually build up this code. So this is, I think, a bit less performant than cassette. Cassette is doing it directly on the code info objects, which is quicker, but yeah, more difficult to handle. And the IRTools now have this easier intermediate representation to work with, but hence it's a little bit more complicated to construct the codes, because finally it again needs to be translated to Julia's standard intermediate representations. But second time is blazingly fast. It's just constructing the code, which takes a bit longer. Okay, and it worked. So now we really get recursively into everything because of the very same logic like we've seen for cassette. And this is just that you've seen it another support. The code ER also supports a two syntax version where you put the Dynamo as a first argument, and as a second argument the function call. And this way you can also inspect the return version. So yeah, so the original one would be my overdub, this one. But yeah, it's sometimes easier, or yeah, and it's good to know. And you see kind of the very simple call. Yeah, our prod call is calling a couple of methods, and we are recursively passing everything to my overdub. Yeah, and then it's using this prod method, and then in there we are going to use again my overdub, and somewhere we hit our special case where we have a multiplication function, and instead we return a plus function. Okay, it's 8 o'clock. Thank you for being there. This was my little introduction to the meta programming stuff here. There's a question already, but let me sum it up and then go to the question. So congratulations to staying here up to the end. So this was a couple of deep dive things here and there, but now you've seen kind of how you can build your own cassette-like meta programming functionality, so that you see you can really hack into code and redefine it. And with this recursive overwriting style, you can really completely reload your code and give it a different meaning. So this is super powerful, but also a bit dangerous here and there. So be careful. And one example, just to see what it means to do metaprogramming, I first tried it the other way around, replacing plus with multiplication. And then I went into an infinite recursion. So my whole computer froze, because somewhere in there, there was an iterator which increased its state by adding +1. And yeah, replacing plus everywhere with multiplication, a +1 is actually not doing anything any longer. And it was a bit difficult to spot this down, so that this is actually what's going on, why everything freezes out of a sudden. So yeah, this is just one example. Many things can go wrong here. But still, it's impressive part of the language. Just-in-time compilation, just at its best, really flexible, but hard to conquer. So I hope you got a lot of insights, some interesting parts to Julia. Here's some further documentations. The Julia documentation itself, expression parsers, my package, the macro tools. Cassette docs has more details. IRTools has also more details. And with that, I want to thank you. And I'm there for further questions. Okay, so there's one further question. The IR, the intermediate representation in IRTools, is used instead of Julia's default IR. Does the compile stage uses one rather than the other, or if you use IRTools, both IR are created? Yeah, so far as I understood it, it's really the second. So I'm not into the details, but the intermediate representation of IRTools is another representation which is built up by IRTools itself. And so far as I know, the only way to do this is to get it from the code info object. And in the sense, it also needs to be retranslated into the code info object. But it's usually not so much of an overhead, because or at least I think this is my heuristic actually, because it's used in Zygote. I think if it would be too much of an overhead, it wouldn't be used there any longer. So you can be relatively safe with respect to the performance part. Yeah, I think this is the best shortcut argument for it.
Thanks. And thanks for the talk. That was pretty intense for an hour and a half. Appreciate it.
Thank you so much. I'm also happy to share my detailed knowledge about Julia here and there, and I think this is one of it. Yeah.
I got to run. Thank you. Bye-bye.
Thank you for your nice words. Yeah. Have a good evening. Bye.